Okay, it's time to get started. Hopefully you had a good and relaxing Labor Day while those of us labored who had to catch up, because Labor Day, I think, is designed for people with jobs to go to work and get the work done that they can't get done when there's meetings, right? So today we're going to be talking about accelerated motion, and there's not much talk to this. It's mostly just going to be you going through the experiment. So just a little bit of introduction for what we're doing. The equations that we're going to be looking at, we're basically building on what we did last week. Instead of using our bodies, we're going to be using carts on a track. So the carts, these little carts, the track, all set in front of you. The feet aren't on them yet, so you'll have to do some setup. But that's basically the equipment. Notice that I have a sensor. Where's Yafet? Yafet? Okay, let's see. He's coming, he says. Can you use that remote, hit 2, and then call on it, making sure it's pointing at the little thing so it changes the view? And then there we go. Okay, now you're going to have to manually do it. Use the control to lower it a little bit so they can see this. Okay, there. So for people in, people at Southwestern, you'll want to look at the picture of the apparatus here as I point out things there. So we have the motion sensor here, the same motion sensors that you used last class period. And then we have the carts. Notice that I have my feet on the cart. I put them at about 1/3 and 2/3 of the way on the cart to give it fairly equal distribution. When you set up, the first thing you're going to do is want to be level. So to make it level, of course, take that out. And it should be close to level. But if it's not level, it'll make a difference. Because, of course, if it's not level, we know the gravity's going to make things come down. So this is where I use the same ball bearings that we used in the first lab. Just place it on here in the middle. And if it's level, it should stay pretty much where it is. Now, you see that time it rolled back. When we did it before, it didn't roll at all. If it doesn't roll, it's got to be reasonably level. If it rolls, well, then you know which side you need to raise or lower until you get it so it stays there in the center of the track level. Now, these tracks, Pasco advertises them as low friction tracks. What does that mean to be low friction? Well, it has some friction. Back when I was in college, we had air tracks, where you had something that was kind of like a V shape, and you connected a blower to it, and it had little holes that would blow out air out of those holes from the blower. And then you had a little cart that, of course, was shaped like a V to fit over it, and the air blowing up would make it levitate. It was very much like the air hockey tables we play air hockey on. And the goal of that was to make lower friction yet. So that was really low friction. It still had some air resistance, but it was really low. This is higher. Pasco has tried to advertise it as, that's a positive that this has real friction, because then you see real life behavior instead of idealized behavior. I don't know, I could see idealized behavior being a good thing, but it is good to realize that there is some realism there. So you're going to set up your equipment so it looks like this. You have your interface. Sadly, few people at the front table, your interface failed this weekend. So you're going to have to use the old style. But you have the interface, you plug your motion sensor into it. With the motion sensor, make sure that you have it set now to the cart setting, and you want to set it so it's looking parallel to the track. On the side of the motion sensor, it has a dial indicator. It should be straight up on 0 for it to be parallel to the track. One last thing of note, these were not designed perfectly. There is a little piece of plastic here that's supposed to grip the track. So the track is supposed to go underneath this ledge and above that plastic. But it's kind of hard often to get it on there. So I was really lucky there. It slipped on nicely. Sometimes you really have to sit there and manhandle it. Just, get it in there. But make sure you're in the right place first so you don't break something. That's good enough for our setup. So go ahead and do now one call, and you can change back to looking at the screen at Southwestern. So the equations we're going to be looking at today, should just be able to put one call and it goes right to it. There we go. Yeah. The equations we're going to be looking at are the relationship between position and velocity, my latest trick, this equation, and velocity and acceleration, that equation. Yes, question.
Can we see what you're writing?
Sorry, that's my bad. I had it set up for us pre-lab, and I forgot that I had that. So what were those equations I was circling? This one here and this one here. So those are the equations we're working with. We're not doing anything numerical with them. That is, we're not going to actually calculate numbers with them. The computer is going to do all of the calculation for us. So you're not going to have any sample equations or anything like that, but those are the equations we're using. So you should have those listed as your two equations. So let's just get right into the experiment. We've already talked about the relationship between velocity, acceleration, position, all of these. So the first thing you do is you level the track like I talked about, and then you're going to make some predictions. So before you ever do an experiment, you're going to make some predictions. And those predictions are going to be, what do the three graphs that you're going to make look like? What three graphs? Glad you asked, if of course you had. Those three graphs are the graphs that we see in the Capstone software. One is position versus time, one is velocity versus time, and one is acceleration versus time, all of them versus time. Notice these are synchronized in time, so you will just be marking your three sets, your position, velocity, and acceleration as a function of time. Make sure you have nice big graphs. Make them so they're, filling up like the width of the page and half a page, because you have three different lines here. We don't want little tiny postage stamp approximations. And on those, you're going to draw what you think they're going to look like. So you'll have to sit there and think, now, what do I think position versus time is going to look like if I have a flat track and I just have the cart go away from me across the track at a low speed? And then you're going to need to give your reason why you chose that shape. And then what's the velocity, or the speed is one-dimensional. What's the speed going to look like as it's moving away slowly? What's the acceleration going to look like as it's moving away slowly? Now, don't try to say, well, there's going to be some random bad data, so let me put that in. Just make it like, if the data is perfect, what should it look like? After you have those drawn, then you're going to actually do the trial. So you're going to actually do a trial with it going slowly away, and then on your three sets of graphs that you already made, using something to differentiate, you'll now draw what it actually looked like instead of what you thought it would. And then you answer, did it look like you thought it would? If not, why not? Well, where were you wrong? Why were you wrong? Right? The purpose of this, the purpose of having those predictions before you do it, is so you have to think about, this is my current understanding. And then after you do the experiment, you'll have either confirmation that you were understanding correctly, or that cognitive dissonance that occurs when you find that what you were thinking would happen is not the same as what happened. In either case, it's designed here to help you learn the process. So if you, shall I say, cheat, if you do the experiment first and then make a prediction so that it looks like your experiment, you didn't learn the things, right? You only saw what it does, but didn't think about the whys, and the physics is about the whys. Okay, so you have your first trials going slowly back and forth. Then you're just going to speed it up. The first ones were going slowly, so they just go across. Then the second ones, you'll want to go quickly, so you'll, give it a nice shove so it comes over here. Notice it's not going super fast, and going back. Now, when you're doing these, don't let it do that. Don't let it crash into my detector, okay? You have two partners. One partner, if it's coming this way, should catch it before it gets to the detector. The other partner is starting and stopping. You want to start it right after they push it. Don't start it before they push it, because we don't want to see that data. Now, granted, if you collect that data, you can scale your graphs to take it off, but it's just cleaner if you just start it after it's moving, because that's what we care about. Stop it before it gets to the end if it's going that way, before they catch it here. One thing to be aware of it, when Yafet and I were doing this before lab, Yafet got ready to catch it, so he puts his hand out here to get ready to catch it. There's a problem. What's that problem? Yeah, it's in the way. So now my detector picked up his hand, so the data went like that. So be careful on that. Don't be an early bird, a farmer boy, as we used to call it when we were playing rook back in high school. You don't want to count your chickens before they hatch. Or in the case of our family, since the almond, we'll be harvesting almonds within a week or two. We don't want to count our crop before we actually harvest it, right? Yes, we are almond farmers with all of 40 acres. Kind of small operation, but it pays well. Okay, so you do it quickly both directions, and then you print, and remember how the printing goes. You print your graph with it going forward and backward. You have some questions about what's the difference for the three graphs going forward versus backward. And that actually takes us to, I don't know, the 2/3 way of the experiment. Oh, there's one thing I forgot that I need to show you. Calibrating the sensors. For this one here, we're actually going to go ahead and calibrate the sensors. Now, the sensors work simply by sending out an audio signal. It's 50,000 hertz, so we can't hear it, and then the reflection back. But you need to know the speed of sound in order to do this correctly. So to get the speed of sound, we will simply use this equation. Okay, so there's an equation. Actually, you're going to use both of those that you're actually going to use. Now, they're not complicated equations, but they're equations you're going to use. How do you get the temperature? Walk right on over here where we have a thermostat, and it says, at this moment in time, a certain temperature. So you'll just, when you're getting ready, go over there, read that temperature, calculate what it is in Celsius because it shows it in Fahrenheit, and then from the Celsius temperature, calculate the speed of sound. Let's say that we have 20 degrees Celsius is the temperature in here. It's not, but it's close. If it's 20 degrees Celsius, then we would have 20 degrees Celsius times 0.606. Of course, 2 times 6 is 12. So that's going to be adding 12.12, 12.12 to 331.3. So that'd be 343.42. So I would have, that would be my theoretical speed of sound if it was 20 degrees Celsius. How many decimal places should I actually have? How many significant digits are in that number? If I measure it 20 degrees Celsius, good to just 2 significant digits, how many significant digits do I have in that speed? Not 2. What do you say, Aaron? 5. Not 5. It's 4. It's 4 because if I have 2 significant digits in this speed, or that temperature, then my 0.606 times 20 degrees is going to have 2 significant digits. So that number that I said is, actually, wait a minute. Whoever said 3 was right. I didn't think about my numbers. I thought it was going to be tens or units and then numbers. So it's 12.12, but only 2 digits are significant. So only the 12 is significant. And so if only the 12 is significant, then I have the least significant digit in this number is that 2, which is going to be the greatest of my least significant digits. And so I add them together as actually only 3 significant digits. Now, if you have a third digit, and you will have a third digit, then you'll have 4 digits for your significant digits there. But just some practice, and hey, I made a mistake too. Didn't mean to. Sorry. Okay, so we have that speed. Now we need to do the calibration. So notice here we have instructions. And the instructions say, click the data summary tab on Capstone, and then the gear icon next to the motion sensor. So let's do that. Data summary, and then this little gear next to motion sensor. And there it has the speed of sound. So now I would need to delete a bunch of numbers and put in 343 there. I think that's 343. I've got to check to see what it put in. Nope. Not that it matters so much for what I'm doing here, but it will for you. For some reason, it wants to put a decimal in front of my... $343. Please accept that. I'm going to trust it didn't go on. So that's how you're going to do the calibration. You put in that speed, and then it's going to have the correct calibration for your sensor. Okay, so we've already gone through all of the level track here. Make sure you answer questions as you go on. Then we have the tilted track. So the tilted track, it says to put your textbook under it. Of course, I wrote this back when you had textbooks. You don't have a textbook anymore. So find something that is no taller than 2 inches. Right? We don't want a really steep track. I initially had people putting them so they were, something like this. Well, to make it come up near the top, you have to go pretty fast. And then it's coming down pretty fast. We don't want to go in that fast, so make sure that the thing you put under here is no more than 2 inches tall. And you can, of course, adjust the angle some more by adjusting the position of these feet. So if I slide the feet farther to the end and use the same support, it's not as steep as it was before. So you can adjust the angle like that. And then before you do any experiment, you have to answer 8 questions. You're going to have the cards go up. And so you'll need to practice how hard do I have to push it to make it go most of the way up the track, at least a meter up the track. Okay, the track's 2.2 meters. If it goes at least halfway up the track, that's enough. I don't want you just going up 4 inches and coming back down. Right, so practice your push a little. And then you're going to answer what does the velocity and acceleration. These are just directions. So you're going to have going up at top, coming down. What are the values for each one of those? That's basically what those questions are asking you. And your answers are only going to be positive, 0, or negative. Right? So it's not very complicated, but make sure you write down what you think each one's going to be and your reasoning. And these questions here are focusing all on velocity on this page. So 4 through 7 are on velocity. 8 through 11 are on acceleration. Then you're going to do your experiment. Your experiment is just one trial. You don't need to do 3 trials on anything today. Just one trial of, as soon as you flick it, start it, go up at least halfway, let it come down and catch it just before it hits, and stop it just before you catch it. And then you're going to be graphing, well, the computer's going to be graphing for you, the position, velocity, and acceleration as it was doing that, and you're going to analyze it. Now, let's just make up some data by myself. So my data is going to be goofy as all get out. Right? Nothing like the reality, because I don't want people to say, oh, that's what it's going to look like. I'm going to answer based on what he did. Okay, so I have this data. You want to scale it so it fills the axes. Don't print it, so you don't fill it. Especially if concern is going to be the acceleration one. Now, with the acceleration, you shouldn't have all of the goofiness that was caused by me, but you will have some errant points. It just happens in data. So if I'm going to scale this, I'm actually going to not just use the auto scale function. Okay, I didn't even see a change with that. I'm going to scale it manually using the numbers here so that I can see what's going on to the non-errant data. Now, your data is not going to have all of the stuff mine had. But scale it so you can really see what's going on with the acceleration. You should see essentially a line for the first half and a different line for the second half. So if you can't see those, you didn't zoom in enough, or maybe you zoomed in too far and you can't see the data at all. But you have to use some thinking there, some reasoning for scaling those. And your data should fill the screen. So like with your, well, that's true of every graph you make. But just pointing this out, I talked to Yafet and he said most people had the scaling done appropriately and some people wasn't close. One thing that slays me is when you see people, start with this. When you see people who scale it, something like that, and say it was a flat line. And really, I've had lots of people do that, not just one person. Maybe you'll have an errant data point that's up here, so the computer automatically scales it. So you just see that errant data point and then a flat line. They say, oh, it was a flat line, moving on. Never crosses their mind to think about the process or how that would be wrong. That thinking is an important part of what we're doing. Okay, back to the end of the lab. At this point, you're done with the experiment, but there's one more section in the lab, and that is applying what you saw, what you observed with the inclined track to a falling ball. Why would we do something like this? Well, that is, in fact, what Galileo Galilei did. Galileo probably never dropped a ball off the Leaning Tower of Pisa, but he did lots of experiments like this. He didn't have the sophisticated equipment we had to make the measurements, but using what timing abilities he had, he did lots of experiments like this and then used that to extrapolate to what would happen if you had a ball falling. And so that's why there's the last part. There's no experiment for the last part. It's applying what you saw. Any questions? I'm sitting here the whole time looking at me instead of looking at my students in the other classroom. That was genius of me. Any questions out there at Southwestern? I see, oh man, I can't remember his name. Mr. Manawa, shaking his head no. Trying to learn your names, you know. Okay, so that's it for our introduction. We're ready to begin. 2 people in a group. We'll have, again, 10 groups in this room, 4 groups in the other room.